Okay, so we have a bit of new material to get through before I can assign any new problems. So I'm going to just sort of chug over the next couple of classes to try to get to that point. Um, so the next topic is rigid body kinetics. Up until now, we've been treating everything as a particle. So there's some new things. Now, objects will have length dimensions. And we will be able to take orientation into account. And rigid body kinetics can happen in 2D or 3D. We're going to be doing it in 2D. Yes, I would say that they go hand in hand because there's no way to distinguish one spot in a body from another if you're treating it as a particle. And if all the forces are acting at the same point, there's no moments either. So now we're going to start talking about moments. So the 2D thing, we're talking about objects, so now we're thinking about something like this, but we're only talking about how it moves in a plane, and it can change its orientation as it changes its position. A lot of times, with a lot of things in physics and mechanics, going from 2D to 3D is a really simple idea. Like it's really just adding, one or two more variables into your equations. This is different from that. Actually, going to 3D makes this super, super complicated. And hopefully at the end, we'll have time for me to sort of do just a little thing about how you would extend this to 3D. But I'll try to bring up the differences as we go through this to sort of point out where the pitfalls come in, if you try to take this to 3D. Okay, so for rigid body kinetics, well, first let's think about particle kinetics. What's the equation of motion in particle kinetics that relates kinematics to the causes of motion? Newton's second law, yep. So now with rigid bodies, we have two equations of motion. The first one is still Newton's second law. And that says that if you add up all the forces on the chosen body, so F net, that's equal to the mass of the chosen body times the acceleration of its center of mass. Specifying the center of mass was kind of redundant when we're talking about particles because a particle we treat as only existing at the center of mass. But now we have to be very careful about the fact that we're doing calculations involving the center of mass. Because if you have a body going, changing orientation as it moves, the different points on the body have different accelerations. If it's rotating like in a circle, when this point at the top going in a circle like this has an acceleration down, the point at the bottom has an acceleration up. They can't both be equal to the net force divided by the mass, So you need to specify one point where Newton's second law holds. So that's the first equation of motion. And in 2D, that gives how many equations? So that's two equations in 2D. And then the second equation of motion is what I call the rotational version of Newton's second law. That's the moment equation. And that says if you add up all the moments, yeah, add up all the moments about point A, so I'll call that MA net. That's equal to the mass moment of inertia about A times the angular acceleration vector of the body. Yeah.
So the N stands for mass?
That stands for moment. In physics, you might have seen that as a tau for torque. In engineering, a torque is a very specific combination of moments, and so we're going to call it capital M, moment.
And then the subscript A.
That's the about point. And in 2 dimensions, how many useful equations does a rotational equation give you? If you're working in 2D, how many useful equations do you get out of any angular equation? 1. Yep, because there's only one plane that it can rotate in. It's either positive or negative. So this is one useful equation. And so for all of these planar problems, a single rigid body is going to give us 3 useful equations. Now, okay, so most people in here have taken statics. In statics, the way this works for rigid bodies is you have F net is equal to the 0 vector, and the sum of the moments is equal to 0. What are your options when you're choosing an about point in statics? Well, we're talking about 2D. So say that you have a, let's see, so look at this in 2D. Okay. Say that you're trying to do the statics of this screen just in a plane, the plane that you're looking at. Where can you put the about point and use that moment equation? Can you put it left corner on my side? Okay, so yes, but do you have any other options? That's kind of what? Anywhere, yeah. Okay, so and you're right that there is probably a best place that makes the math the easiest, but the key thing in statics is that anywhere you want, you can put the about point. And one of the just couple of things that I don't like about doing statics before dynamics is that it gives you a bad habit in this sense. You get this sense that you can put this about point anywhere you want. If the thing is moving, all of a sudden there are only 2 possibilities for where you can choose your about point. So for the rotational Newton's second law, this about point A has to be either a fixed point in the coordinate system. So by a fixed point, I'm talking about like a joint between the body and the ground. So a place on the body that's held fixed to the coordinate system. Or you only have one other option, and that's the body's center of mass. Those are the only 2 that you can choose. And is there any law saying that whatever rigid body you're looking at has a point that's fixed to your coordinate system? No, like if this rigid body is flying through the air. There's no point on it that's fixed the way it would be if there was like a joint connecting it to the ground. Okay, so this doesn't always exist. Okay, the center of mass always does exist, so you could just always put the about point at the center of mass, but it's also always more like there's more math involved when your about point is the center of mass. So this always exists, but it requires doing more math than if your about point is at a fixed point. Okay, so we're going to see, we'll have a lot of views, like it'll be easy for us to see as we go on what are the benefits of having your about point be at a fixed point if it's possible. Otherwise, we just say, well, forget about the fixed point, just always do it the same way at the center of mass. But you get a nice benefit out of doing it at the fixed point if you can find it. Okay, so what does this tell us? So there are three new things we have to define. Three new things we need to define before we can do rigid body kinetics problems. The first one is the center of mass. That's easy for very symmetric shapes, squares and rectangles and circles. You have a pretty good sense of what that is. The centroid, the center of mass, is just the geometric center of it. But for more complicated shapes, we're going to have to actually calculate that. The second thing that we're going to have to define is that mass moment of inertia. That's the thing in the rotational Newton's second law, capital I sub A. And you can think of that as sort of the rotational version of mass. It's a body's resistance to having a rotation started or stopped. And then the third thing is the moment. I'll call this the moment of a force. We'll call that capital M sub A. In both 2 and 3, both of those cases, that A refers to the about point. And if you look at that rotational version of Newton's second law, notice that, we've been dealing with angular acceleration, so maybe this isn't a surprise, but this moment has an about point. You can't define a moment without an about point. You can't define the moment of inertia without an about point, but angular acceleration does not depend on an about point. Okay, that just has to do with how quickly the front of something is changing. Yep. Yes. And they both have, they have to be the same. So they both have to meet those two, one of those two requirements. Okay, so let's start with defining the center of mass.
Is that mass moment or is that a vector?
That is an important question. For us, it's going to be a scalar. But when you go to 3 dimensions, it turns out it's not a vector, it's a matrix. It's a 3 by 3 matrix. Yeah, well, if we get to it, we will. But we have enough to worry about before doing that, you know what I mean? Oh, and actually, this moment of a force, though, that is a vector. So put the vector symbol over that. Okay, so center of mass. So the integral definition of center of mass, you know, there are integral definitions for the center of mass and the centroid. We're not really going to use those, but I'm going to give you those. And maybe I'll come back and do an example, so you just see one example of how to use this. But the integral definition of center of mass. In 2D, so this is the position vector of the center of mass. It's so you choose a coordinate system, and this would be the coordinates of the center of mass are equal to 1 over the total mass times the integral over the whole body, over that whole mass, of the xy positions of some infinitesimal increment of mass times dm. And in 3D, the only thing that changes is that we have 3 of these coordinates instead of 2. So we'd be calculating the x, y, and z coordinates. And that's equal to 1 over the total mass times the integral over the whole mass of x, y, z, dm. The integral over the, so the like the boundaries of the integral, if you think of it as a definite integral, are going over the whole body. So like for example, in 2D, if you're trying to figure out the centroid of a right triangle, you break it up into little slivers. This infinitesimal sliver has some mass, you know, some infinitesimal mass. And then you go through just the, you know, kind of the definition of the integral derivation. Usually we're not going to think of it this way. If the body is homogeneous and so homogeneous means that it's the same material everywhere. So this, okay. So if the body is homogeneous, the center of mass is the centroid. Think of as just the geometric center of the object. Yeah, we are only going to deal with homogeneous. And so for this in 2D, so to calculate, the notation that you use for this is the centroid is shown by an overbar. So let's say x bar, y bar, that's the centroid of an object, is equal to 1 over the total area times the integral over the area of xy dA. Okay, so you can imagine, so say that we're calculating the geometric center of a disk, okay? That's going to end up exactly where you think it would be, right in the middle. But if this disk had one part of it over here that was steel and the rest of it was wood, the center of mass would not be in the same place as the geometric center. So that's how homogeneity is required for that connection to be made. So this is true for homogeneous, and in 2D, for this 2D version, it also has to be, it also requires uniform thickness. Okay, so yes. Mm-hmm. I'll be the judge of that. Oh. So for, yeah, I mean, I guess there's not really like an overall answer to that because it just depends on what kind of precision you need. Like at some level, nothing's exactly homogeneous. But if, so reinforced concrete that's a good question. That probably, if you're dealing with a small amount of it, then this won't work. If you're dealing with a really big amount of it, it will work, but it just comes down to the amount of precision you need. We'll see that, so the way you would probably do that if you were dealing with a sort of a small non-homogeneous material, okay? So then you can't use this centroid idea. The way you'd actually do it is you'd treat all the stuff, you take all the concrete in one chunk, and you'd calculate the centroid of that and calculate its mass. And then you'd take the steel and calculate the centroid of that and then consider its mass. And then you'd use a sum formula that I'll give you later yeah. All right, so that's the 2D centroid formula. The 3D centroid formula is like this. So again, it's x bar, y bar, z bar. In this case, it's not quite as simple as just adding a third component. You also now, where we were talking about area for the 2D, now we're talking about volume. So 1 over the total volume times the integral over the whole volume of x, y, z, d volume. It's not ideal to have to use these integral formulas every time you want to calculate a centroid. So really what we're going to do is, for just about any shape you can think of, if there's a way to come up with the general dimensions of a shape, then only one person really had to do the integral formula. And from there, we have a formula that relates the centroid to the dimensions. And so I'm just going to give you a list of, common shapes and the way to calculate where that centroid is. There are also, besides those common shapes, there are also 2 other facts that are going to make this easier for us. So here are 2 facts that often simplify centroid calculations. The first one is if you can find, so if the shape that you're interested in has a line of symmetry, that's if you're talking about 2D, or a plane of symmetry if you're talking about 3D, then the centroid has to lie on that line or plane. So the centroid lies on that line or plane. Okay, so like for example, a shape like this, like the Star Trek communicator, that only has one line of symmetry, but it does have one, right? If you, and for a line of symmetry, you can just think of like cutting out that shape and folding it, and if it matches up, that's a line of symmetry. And so the centroid has to lie on this one. That doesn't tell you where the centroid is, because you still have to figure out where along this line it lies. But it's already cut down the number of calculations you have to do in half. Okay. And then if you have shapes that have more than one line of symmetry, like a rectangle or a circle, so this has a line of symmetry this way, and a line of symmetry this way. Well, it has to lie on both of those, so that means that the centroid is where those intersect. And a circle has infinitely many lines of symmetry, but they all cross at the same point. And so the centroid has to be where they all cross. Any questions about that? So to do this in 3D, you need to do it with planes of symmetry. I'm not going to draw that, but I mean, any 2D shape is really, if you're talking about an actual object, it's really a 3D object. So you can imagine that in 3D, if this just extends some uniform thickness into the board, this line of symmetry is really a plane that cuts it. And so, and then if you think of a sphere, instead of lines of symmetry of a sphere, you can cut it with all these different planes, and it works out just the same way that this does. Those planes, all these different directions, they all have one point in common right at the center, and so that has to be the centroid. Okay, the second thing that's really useful, maybe even more useful than this first one, is that if a complicated shape is made up of a combination of simple shapes, so for example, if you're trying to calculate the centroid of something like this, okay, well, there's no table anywhere that gives you a formula for the centroid of that shape. But you can break this shape up into a rectangle here. There's a few ways you could break it up. And so now that complicated shape is made up of 4 rectangles. And if you know the centroids of those individual shapes, then the centroid of the complicated shape is equal to 1 over the total area, or you can think of this as, well, let's just write total area, times the sum of the area of the individual shape times the centroid of the individual shape.
What are the lines above?
Centroid. So what that says is in whatever coordinate system you're in, if you want to calculate the centroid of this thing, the way you do it is find in that coordinate system the centroid of each of these 4 individual pieces and figure out the area of each of those 4 individual pieces. And then 1 over the sum of the areas times the sum of each piece's area times its centroid. It's sort of like a weighted average. And by the way, if you look at that formula and compare it to the integral definition, it has exactly the same form. It's just like when you go from the limit of an area to a finite approximation of an integral, you switch from the Riemann sum, the integral, to a sum of, this stands in for the dA, the infinitesimal increment of area, and this stands in for the position of that dA. This has a line of symmetry, by the way. Which direction is the line of symmetry, horizontal or vertical? Okay, so that means that we know the height, right? And so we don't have to do this as 2 dimensions. We can just use the x equation from this to calculate the horizontal position of the centroid. You can do the same thing in 3D. And it works just like you would think it would. So x bar, y bar, z bar is equal to 1 over the total volume times the sum of, for each of these bodies, the volume of the individual, simple shape times the centroid of that individual simple shape. And by the way, I'll do examples like this, but these work with subtraction and addition. Addition and subtraction. So just like we could, the quickest way to do this is, I don't know, this might actually be quicker. So we thought of that as adding up, using this sum formula to add up this shape plus this plus this plus this. But you could also think of it as adding this shape to this big rectangle and then just subtracting this small rectangle. Okay. And so in that case, you would do, so for this little shape, you do its area times the centroid of that shape. For the big one, you do the centroid of this big rectangle times its area. And then for this one, you'd say minus the area of what you're removing times the centroid of the thing you're removing. Okay, we'll do an example like that. Okay, so the last thing I have to do is just give you the formulas for some of the simple shapes that we'll use. You can imagine, I'm sure that like if you think of a rectangle as the basic simple shape, this is sort of the idea that you used in defining integrals too. You could, whatever complicated shape you want, you could approximate that as, you know, 1,000,000 or 1,000 or 100 or whatever rectangles, depending on how much precision you need. So really by just knowing how to do the centroids of rectangles and knowing that sum formula, you could write, say, a computer program that would approximate any shape, you know, the centroid of any shape you want. In a way, that's the only thing you need. But I'll give you this for some common shapes. Okay, so here are centroid formulas. For some common 2D shapes. The first one is a quarter circle. And the centroid is that would have been a very rude comment. Okay, so here's the centroid. And so we're going to think of this distance as our x bar, and this distance is our y bar. And for each of these, I'm going to give you the x bar formula, the y bar formula, and the area formula. And the reason you need that area formula is so that you can use these simple shapes with the sum formula. All right, well, x bar is 4r over 3 pi. There's a symmetry here, so the y bar formula has to be the same. And then the area is just a quarter of the area for a circle, so pi r squared over 4. Second, a semicircle. Well, you could easily use the sum formula to figure out that the vertical location of the centroid of a semicircle is the same as the vertical location for a quarter circle. But I'm going to give you this one since it's going to come up pretty often. Okay, so first of all, well, the centroid is here. Notice first that it has to lie on this line of symmetry. So we don't really need to have a formula for x bar. We know it's going to be in the middle. The only question is the y bar. And the formula for this y bar, so we'll forget about the x one. You can just do that by inspection. But y bar is the same as it was for the quarter circle, 4r over 3 pi. And then the area is pi r squared over 2. And then the last shape that we need is a right triangle. Okay, so this is 90 degrees. And we're going to measure our x bar from the flat side and our y bar from the flat side. And the dimensions of this triangle we need to give. So we'll say that this is h and this is b. Then the formula for the x centroid is b over 3. The formula for the y centroid is h over 3. And the area is base times height over 2. Rectangles and full circles are going to come up all the time too, but we don't need formulas for those because they have multiple symmetries, and so you can just find the, just look and see where the center is. Yes. Well, okay, so that brings up kind of an important thing about how you're going to have to use these. All of these things I've given, they sort of, like maybe this notation isn't the best because it looks like those are coordinates, but you need to just think of those as distances. And so, like, for example, sometimes, this quarter circle could be turned the other direction, and the origin could be way over here somewhere. And you're just going to have to use those distances to figure out, what the coordinates are. Okay, so let's do a quick example.
So X bar and Y bar are not coordinates.
That's right, they're distances. Yep. I mean, coordinates are also distances, but these don't take any direction into account. Okay, so let's do so let's figure out the centroid of Minnesota. Will approximate Minnesota. That's supposed to be a semicircle. And we'll say this is 400 miles. We'll say this is 400 miles. And so the way we're going to get this is, you can think of this as a square with a side length of 400 miles, and we've removed a semicircle from it. So this semicircle has a radius of 200 miles. Okay. In order to figure out where the centroid is, come up with coordinates for it. We're going to have to choose a coordinate system, choose an origin location. The simplest one would probably be to put it here in Lake Worthington. Okay. we know that there is a line of symmetry. And so we know that from symmetry, y bar is equal to positive 200. That really could not be more annoying. Okay, so y bar is 200 miles. So all we need to calculate is x bar. And the way we're going to do that, we have to, so we're going to think of this as a square with a semicircle removed. So for the square, x bar is 200, right? The area, so I'll call this sub S cubed. The area is 400 times 400, so that is 16 times 10 to the 4. So that's 160,000 square miles. Now for the semicircle, we can use the formula for the semicircle. And notice that the semicircle that we have is flipped sideways. And what's given is the distance from the flat side, the cutoff side, to the centroid. So what this gives us, this formula 4r over 3 pi, is the distance from here into the centroid of that thing. You see that? Okay, so 4r over 3 pi is 4 times 200 divided by 3 pi, and that is so that's about 84.89, I think. But that's not the coordinate. That's the distance from here going the other direction. Okay. Well, so what we want to do is it's going to be 400 from here to there. And then we're going to subtract 84. So x bar for the semicircle is 400 minus 84.89. And so you get 315.11. And then the area is pi r squared over 2. That comes out to about 62,831.
Why don't we, I guess, if I were just gonna do it intuitively, I would do 200 as. The E4 represents the centroid, right?
Let me just finish this and then we can talk about that after class, okay? So now the formula says x bar is equal to 1 over the total area. So that's 1 over 160,000 minus 62,831 since we're removing this material, times the area of the square, which was 160,000, times the centroid of the square, which was 200, minus 62,831, the area of the semicircle, times the centroid of the semicircle, which was 315.11, and you get that x bar is about 126. So in other words, to get from Worthington to the centroid of Minnesota, you go 126 miles east and 200 miles north. Any questions about that? So that centroid, that means, is somewhere over here. Okay, that's all. Well, we made it a coordinate, but we used the formula to come up with coordinates. But you have to think of the numbers that come from those formulas are just distances from some reference point towards some other reference point.